We're going to start with exponential equations. I actually think that this is the more challenging of the two because there are more options on what an exponential equation could look like versus a logarithmic equation. I want to start by introducing the one-to-one property for exponential equations. This property says if b to the x is equal to b to the y, then x is equal to y. Basically, what it's saying is that if you can rewrite your equation so that you have like one term on each side of the equation, if each of those terms can be rewritten as the same exponential base, then all you need to do is set the exponents equal to each other. Our general strategy for solving exponential equations, well, try to make one-to-one property work because that's definitely the easier of the techniques is to use the one-to-one property. So if both sides can be written as exponentials with the same base, do that and then apply the one-to-one property where basically you're setting the exponents equal to each other. Now, that works less times than it doesn't. So we need to have a plan B. If we can't use the one-to-one property, we want to write the equation in logarithmic form to get the variable out of the exponent and solve the resulting equation. Both of these techniques, that's what we're trying to do. We're trying to get the variable out of the exponent so that we can solve for it. So here goes. Let's solve 2 to the x minus 1 equals 8. We want to find the exact answer and then an estimate answer that's rounded to the nearest thousandth. I start by noticing that I have just one thing equal to one thing, so maybe that one-to-one property will apply. We want to try to rewrite both sides as the same exponential base. So I usually start with the big base and say, can I rewrite it as the little base? So can 8 be rewritten as 2 raised to some power?
Yes.
Sure can, right? That's 2 to the third power. Now that I have the same exponential bases, our one-to-one property tells us that our exponents have to be the same. So all we're going to do is set the exponents equal to each other and solve. We get x to be equal to 4. Questions at all? All right, next up, let's solve 4 to the x equals 32. We've got just one term on either side, so I might be able to use the one-to-one property. I always start by looking at the big number and seeing if it can be rewritten in terms of the small number. So can we rewrite 32 as 4 raised to some power? Nope. But before I give up on the one-to-one property, I'm going to see if I can rewrite that 4 as some other number raised to a power and then see if 32 can be rewritten as that other number. So 4, can that be rewritten as some other number raised to a power?
2 squared.
2 squared. So this is going to be 2 squared raised to the x. And when we have a power raised up to a power, we multiply our exponents. All right, well, now we have a base of 2. Let's look at 32. Can 32 be rewritten as 2 raised to some power?
2 to the 5th.
That's 2 to the 5th power. So now we have 2 to the 2x equals 2 to the 5th, and by our one-to-one property, we can set our exponents equal to each other. And we get x to be equal to 5/2. Questions, anybody? right? The one-to-one property is nice. You'll see when we do the other ones, it's way quicker if the one-to-one property can be used. So I strongly encourage you to look for that every single time. Let's solve 6 to the x equals 3 to the x plus 1. So here for the first time, we have variables in exponents on both sides of the equation. But that doesn't mean that one-to-one property can't apply, so I'm still going to try that. I'm going to see if I can rewrite 6 as 3 to some power. But I can't. Can we rewrite 3 as some other number raised to a power? No, I can't do that either. So the one-to-one property is not going to apply to this example. What we're going to have to do instead is rewrite this in logarithmic notation. So typically there's a very specific way that I like to teach this, but the way that MyMathLab likes you to type in your answers is different than the way that I like to teach it. Now, usually I'm not worried about that, but since your final exam will likely be on MyMathLab, I am concerned about you being able to type your answer in correctly on that test. So I'm actually going to show you 2 different ways to do this. The first way, the way I typically prefer to do it, I feel like it makes more sense because we're reinforcing skills that we've already learned. But I will show you both ways so you have them both at your disposal. All right, so we're going to have to rewrite it in logarithmic form. What I like to use is the definition that we've been using, y equals log base b of x is rewritten as b to the y equals x. So same thing that we've been doing when we've been converting back and forth between exponential and logarithmic notation. Typically, when we do this, there's only been an exponent on one of the sides. So we knew what number to take as our base. We can actually take either one. We can rewrite this in terms of log base 6 or log base 3. We'll get the same answer in the end, doesn't make a difference. However, there is one base that would make the algebra work out easier than the other. You want to choose the base that has more terms in the exponent. So I would definitely choose to rewrite this in terms of log base 3. All right, so here goes our logarithmic rewrite. We're going to have log base 3 of 6 to the x equals x plus 1. When solving any equation, no matter what kind it is, we're always trying to gain access to the x. Right? We don't want x in the denominator. We don't want it in parentheses. We don't want it in an exponent. We want x like right on the ground level where it's accessible for us to solve. So that was why we converted from exponential notation to logarithmic notation. Now, one of our 2 x's is accessible, but the other one's not. The other one's actually in a worse spot than it was because not only is it inside of an exponent, not only is it in an exponent, but it's also inside the argument of a log. So we want to get it out of both of those places. We don't want it in the log. We don't want it in the exponent. So we are going to use log property number 7 that says if you have an exponent inside the argument of your log, it comes out in front and becomes a coefficient. It's going to give us x times log base 3 of 6 equals x plus 1. Any questions so far? We're still looking to solve for x. We cannot just subtract 1 from both sides because we cannot have x equals something with an x in it. So we're going to use a technique that we've done before. So notice that I have x showing up more than once and they're both linear. When solving a linear equation, we always want to get x's on one side and constants on the other side. Well, that's true here still, because this is a linear equation. So we want to get all the x's on one side, all the constants on the other. So I'm going to subtract this x over here. But the thing is, I can't combine it with that x times log base 3 of 6. They're not like enough. Yes, they're technically like terms because the same variable to the same exponent, but I can't combine them because of that log base 3 of x. So I'm just going to have to tack it on the end. You'll notice we now have a common factor of x on the left side. So we can factor an x out, leaving us with log base 3 of 6 minus 1 equal to 1. And now the variable that we want to solve for, the x, only shows up a single time. And we can isolate that one and only x by dividing both sides by that stuff in the bracket. And we get x to be equal to 1 over log base 3 of 6 minus 1. And that is our exact answer. So there's our exact answer. Questions at all? All right, well, we also need a decimal approximation rounded to the nearest something, thousandth maybe? Yep, nearest thousand, 3 decimal places out. Because this is log base 3, we're going to have to change a base formula. We get x equals 1 over natural log of 6 divided by natural log of 3 minus 1. I do not have this decimal on my paper, so I'll need you to do this. Plus, I strongly encourage you that you're practicing using your calculator. You don't want to wait until you get to your test and then you can't use your calculator properly. Anybody have an answer?
I have an answer, but I don't know if I put it in right.
Well, that's okay. What'd you get?
I got negative 0.492.
That does not sound correct to me. So be sure that you put this bottom in parentheses when you type it into your calculator. So try it again. We should be getting something closer to like 1.5.
I got 1.58.
Can you take me out one more decimal place?
5.
Yeah, that sounds good to me.
Yeah, I re-put it in and I got that answer now.
Great. Yeah, it's real important we have those parentheses in the denominator. Anybody else? Questions? Anybody having any trouble getting it in their calculator? Yesterday, people were saying, yeah, I'm having trouble, and we'd just wait, and they'd shove their calculator up in the camera, and we'd fix their issue. So please make sure if you have any questions you're asking. All right, so this is the technique that I prefer because I like it so much because we're just reinforcing things that we did before. We're not really learning anything new, and I always like to learn less and apply it more often. But I'm going to do it a second way because frequently the directions on MyMathLab will say, write your answer in terms of common log or natural log only, that they won't let you put something in like 1 over log base 3 of 6 minus 1. So I'm going to show you this second technique as well. Although when my virtual class, they're actually doing all of chapter 4. I didn't cut any material out for them with this whole transition, and I was just really selective about the ones that I chose so it didn't trip people up, but I'd rather show you both ways anyways, even for the homework. So what they like to use is the one-to-one property for logarithms. So I'm going to scroll down here to where our one-to-one property for logs is. Our one-to-one property for logs says that if log base b of x is equal to log base b of y, then x has to be equal to y. So if you have 1 log equal to 1 log, if their bases are the same, then their exponents have to be the same as well. Typically, we go in this direction with the property, and we end up dropping the logs. But you can actually go the other direction as well. If you have two things that are equal to each other, you can make them the argument of a log of the same base. So basically, we can put a log on either side and make what we were given originally the argument of those logs. That's the technique we need to use to pacify MyMathLab. So if I'm starting with 6 to the x equals 3 to the x plus 1 using the one-to-one property, and then we either want to use natural log or common log. I personally prefer natural log. We're going to make these be the argument of a log. So I'm like natural logging both sides. This is the way I was taught when I was a student. I had no idea what I was doing. I could make it work, but I had no idea why it was working. So that's why it's not my preference on teaching it this way. All right, so this becomes natural log of 6 to the x equals the natural log of 3 to the x plus 1. Oh, we're still solving for x, and I still have the issue that the x's I'm solving for are located in the exponents, so I need to get them out of the exponents. We're going to use our log property number 7 again to get these exponents out of the arguments. They're going to become coefficients. we get x times the natural log of 6. Now on the right side, you have to be careful because we're taking that binomial of x plus 1 and bringing it out in front to become like a coefficient. So be sure that you put that x plus 1 in parentheses. Still solving for x. I need my x to be accessible. The one on the left is, but the one on the right is still trapped inside of parentheses. So I'm going to distribute the natural log of 3 on the right to eliminate the parentheses, and now that x is accessible. I've got these two linear x's. We're going to use the same solving technique that we did with the other method. We're going to get all the terms containing x on one side, all the terms that don't have an x on the opposite side. We'll factor out our x and then divide. X times the natural log of 6 minus x times the natural log of 3 equals the natural log of 3. Factoring out the x on the left side, we get the x times the natural log of 6 minus the natural log of 3 equal to the natural log of 3. And lastly, we're ready to divide both sides by the natural log of 6 minus the natural log of 3. We get an exact answer of x equals natural log of 3 divided by natural log of 6 minus natural log of 3. Questions on obtaining that exact answer? One advantage to this technique is when we need to get a decimal approximation, we don't need to use change of base formula because everything's already in terms of the natural log, and we can just plug it in our calculator. And get our answer. So we should end up with the same answer that we did with the other technique when you pop this in your calculator. Questions, anybody? All right, let's try another one. All right, so I'm going to do this both techniques again. I'm going to do one technique where I'm going to use log base 9 since that's the base that has more terms in the exponent, and then I'll do it again using the natural log. Rewriting this in terms of log base 9, we get log base 9 of 8 to the 3x is equal to 2x minus 4. One of the x's is accessible on the right, but the one on the left is not. So we're using log property number 7 and making our exponent a coefficient. We get 3x times log base 9 of 8 equals 2x minus 4. Next, we want to get all of our terms containing an x on one side. So I'm going to have to subtract that 2x over. Cannot be combined with the 3x because the 3x is attached to the log base 9 of 8. We now have a common factor of x on the left side that can be factored out. Leaves us with 3 times log base 9 of 8 minus 2 equals -4. And then lastly, we're ready to divide both sides by all that we have in the brackets. We get an exact answer of x equals -4 divided by 3 times log base 9 of 8 minus 2. Questions at all? We see that they're super repetitive. We're really just going through the same steps over and over and over again. To get our approximate answer, we're going to need to use change of base formula. So that log base 9 of 8 turns into natural log of 8 over natural log of 9, but we kind of got this 3 times out in front. I personally don't like it just hanging out in front, so I'd put it on the top, because remember that's 3 over 1, and when we multiply our fractions, it would go up top. And be sure to put this in brackets when you type it in your calculator. So let me know what you get.
I got -4.77.
We're going to 3 decimal places though. So what'd you get? Like
777
777?
or 767.
I bet it was 767. All right, sounds good to me. Anybody having any trouble typing this into our calculator? Okay, I'm going to do this a second time using the natural log technique instead. We're just going to make our original equation the argument of a log. And we're going to use one that our calculator can do. This gives us the natural log of 9 to the 2x minus 4 equals the natural log of 8 to the 3x. We need to get the x's out of the exponent. So again, we are going to use our log property number 7 and bring these out. The first exponent that we're bringing out is a binomial. Be sure to put it in parentheses, as we'll eventually have to distribute that natural log of 9. We get 2x times the natural log of 9 minus 4 natural log of 9 equals 3x times the natural log of 8. We need to get all our terms containing an x on one side. So let's move that 2x natural log of 9 over to the right. That'll give us -4 times the natural log of 9 equals 3x times the natural log of 8 minus 2x times the natural log of 9. We now have a common factor of x on the right that can be factored out. Leaving us with 3 times the natural log of 8 minus 2 times the natural log of 9. And then we're ready to divide by what we have in the brackets. We get x to be equal to -4 times the natural log of 9 over 3 times the natural log of 8 minus 2 times the natural log of 9. And our approximate answer should be the same as what we got with our other technique. Questions, anybody? All right, so the next one, you'll notice that we have binomials in both exponents. I'm actually going to split you guys into groups and let you work on this one. I don't really care which technique you use, whichever you're more comfortable with, but no, you're going to need that natural log technique for some of the problems on the homework and on the final exam. But I like the first technique because I just feel like we're reinforcing skills that we already have. So I'm going to put you guys into groups, kind of big groups, so you guys can help each other out because this is a tougher kind of problem. And I will check on you in 5 minutes. Show everybody the answers now that we're back together. I did it 3 different ways. I did it log base 2, log base 5, and natural log. They should all be the same decimal approximation. But with this one, you know, log base 2, log base 5, I wouldn't really have a preference because both of those have the same number of terms in the exponents. Anybody, any questions at all? You will definitely be seeing a question similar to this, maybe not with 2 terms in both exponents, but definitely one like this we'll be seeing on the final exam. All right, there is one last type I want to look at with exponentials before we move on to logarithmic equations. Notice for the first time we have an equation that contains 3 terms. in the past, we've been like, oh, well, one term equal to one term, I'm going to be able to use the one-to-one property. Or to rewrite as an exponential, I need one term on each side. Since we have 3 terms, and even if I rearranged it, I'm not going to lose a term, neither of the techniques we've used so far are going to apply here. So we need to do something a little bit different. This is actually an equation that is quadratic in form. You know that something is quadratic in form when you have it set equal to 0 and in descending order. If the second exponent is half the first, then you know that you are quadratic in form, and x is certainly half of 2x. If we're quadratic in form, we can factor this by substitution. We want to start by identifying what our substitution should be. What should we substitute for y? Well, anytime you're doing factor by substitution, your substitution is always the variable portion of your second term. So we are going to substitute y in for e to the x. This will give us the equation y squared minus 4y minus 5 equals 0. And that certainly factors nicely for us. This turns into y minus 5 times y plus 1 equals 0. Once we get through the factoring portion, we want to plug e to the x back in for y. And we'll get e to the x minus 5 times e to the x plus 1 equals 0. Any questions so far? We're ready to apply zero product property then. E to the x minus 5 equals 0, or e to the x plus 1 is equal to 0, and we'll solve each of these equations. Looking at our first one, e to the x minus 5, we want to start by isolating the exponential. So e to the x is equal to 5. One term equal to one term, so this means that I can either try the one-to-one property, and if that doesn't work, just rewrite it as a log. Well, the one-to-one property is never going to work with e. E is an irrational number. We're never going to be able to rewrite another number in terms of that irrational number. So we need to rewrite it in logarithmic form. Our exponential base is e, therefore our logarithmic base is going to be e as well. This turns into the natural log of 5 equal to x. Natural log of 5, this is our exact number, our exact answer. If we want to get an approximate answer, no change of base formula necessary. We can just plug this right into our calculator as is. We get 1.609 for an approximate. We'll do the same steps to solve e to the x plus 1 equals 0. We'll start by isolating the e to the x, and then we'll rewrite it in logarithmic form. Again, log base e, natural log of -1 is equal to x. So that is our exact answer, but what do you know about the natural log of -1? Well, do you know anything in general about the argument of a log? That would be a great, like, short answer question on our test that we're having this week. The argument of a log always has to be positive. So since we have the argument of a log being equal to a negative number, we got to throw out this answer. So we only get one answer, x equals the natural log of 5. Questions, anybody? Okay. We have an application here to solve. The population of a city is P equals 250,342 times e to the 0.012 t power, where t equals 0 represents the population in the year 2000. We want to find when the population will be 320,000. Suggestions on getting started? They want us to figure out when our population will be 320,000. The variable P represents population, so all we need to do is substitute 320,000 in for P and solve for T. Because E is my exponential base, I know that the one-to-one property will not apply. So instead, I'm going to have to rewrite it in logarithmic form. But before I can rewrite it in logarithmic form, I have to isolate the exponential portion. We'll divide both sides by 250,342. This is not going to divide nice. So I would just leave it. We certainly don't want to round on our first move. It might simplify some. I see they're both even, but personally, I wouldn't even waste my time because I'm ultimately going to be plugging these numbers into my calculator. So I would just leave it. Definitely don't convert it to a decimal. Now that we have the exponential portion isolated, we can rewrite it in logarithmic form. This is exponential base b. So we're going to end up with logarithmic base e, which is our natural log. Natural log of this fraction is equal to 0.012t. And then we'll divide both sides by 0.012. We get t to be the natural log, 320,000 over 250,000, 342. All of that divided by 0.012. And let me know what you get. Who has an answer for us? In the chat. Thank you, Victoria. $20.458. But let's go back. I don't even remember what the question was. We want to find when the population will be this 320,000. We just found T, but it tells us that T represents, like T equals 0 represents the population in the year 2000. So if T equals 20 and change, that's going to be that many years after 2000. So to actually answer the question, we're going to take this 2000 plus 20.58. So what year does that make that? If I want the year 2000 plus like 20.458 years, what calendar year does that put us in?
$2020.
So we've gone 20 full years plus almost a half. So just the way that we do our calendar, like we say it's 2020 on January 1st, even though we haven't gone through that whole year yet. So anytime, no matter what these numbers are, so don't think about rounding. If you have any decimals at all, you always want to round up because we've gone 20 full years past 2000 and now we're like halfway into the next year. So it's like May 2021. So always, always round up. That's tricky. And again, it doesn't have to be 5 and over to round up. Even if it's 0.01, you're still rounding up. Questions, anybody? So with 11 minutes left, I don't really want to start log equations, so I'm going to jump to page 225. We're going to discuss exponential growth and decay models, and these are applications of exponential functions, so I'd rather jump to this than start log equations. The mathematical model for exponential growth or decay is a equals a sub 0 times e to the kt power, where a sub 0 is the original amount or size at time t equals 0. A is the amount at some particular time t, and k is a constant representing the growth or the decay. If your k value is positive, then whatever you have is growing, but if your k value is negative, then whatever you're talking about is getting smaller or decaying. That's definitely a formula you're going to need to know. So as you're making whatever kind of outline for the final exam so that you have ready to go for the test, this should definitely be on the list. These problems are extremely similar to the variation problems that we did. Remember those application problems, like the first sentence we'd use to write the general equation. Then we'd plug in the numbers from the second sentence and solve for k and rewrite our equation with the k value in it. And then the third sentence, we would use the equation that we wrote to answer the question that was posed in that third sentence. These problems are extremely similar to that general procedure. The only thing is you don't have to think what the general equation is going to be because we're always going to be using a equals a sub 0 times e to the kt power. In 1990, the population of Africa was 643 million, and by 2000, it had grown to 813 million. We want to find the exponential growth function that models the data in which t is the number of years after 1990. We'll round our k value to 5 decimal places. And then once we've rewritten our equation and we have this model, we're going to use it to answer part B, which asks, by which year will Africa's population reach 2 billion? All right, well, we're going to start by coming up with this exponential growth function. We start with our generic equation, a equals a sub 0 times e to the kt power. We want to plug in the information they've given us and solve for k. So that means I should have a sub 0, and t. A sub 0 is the original amount from our discussion. What is the original amount that we're starting with?
$643,000,000.
Great, so that'll be our a sub 0. Then we need our a, which is our amount after a particular amount of time. So what's our second amount, our grown amount?
813 million.
Great, that'll be our a. And then the last thing we need to know is, well, how much time occurred in between our a sub 0 and our a. Well, right here, it says we went from 1990 to 2000, so that tells us t equals 10. Oh, we're going to plug all this into our equation and solve for k. 813 equals 643 times e to the k times 10 power. I'm going to rewrite my exponent. We're solving an exponential equation. We always want to start by isolating the exponential portion. So let's divide both sides by 643. 643 does not go into 513 nicely, and I certainly don't want to round on my first attempt, so I'm going to leave the fraction. One-to-one property is not going to apply because our exponential base is e. So instead, we want to rewrite it in logarithmic notation. Our logarithmic rewrite will be natural log of 813 over 643 equals 10k. And then we need to divide both sides by 10. We get k to be the natural log of 813 over 643, all that divided by 10. And our directions told us to take k out 5 decimal places. 0.02346. I'm anticipating a positive k value since the population is growing. Right? Things get bigger, positive k. Things are getting smaller, we're going to have a negative k. But we're not quite done for part A. We're supposed to find the exponential growth function that models the data in which t is the number of years after 1990. So we're starting at 1990 always. So that initial amount from 1990 is always going to be there. We can't go back in history and change the population. So we're going to rewrite our general equation, plugging a sub 0 and our k value in. We get a to be equal to 643 times e to the 0.02346 t power. And that's the equation we'll use to answer our question in part B. Questions at all with getting this equation?
Can you plug the natural log that you have there, 813 over 643, all over 10 in the calculator?
Yes. And that's where I got the 0.02346.
Because when I did that, I didn't get that number.
Try it again. Make sure that you have that 813 over 643 in parentheses. How'd it go this time, Eric?
Still didn't get that.
Still didn't?
Nope.
All right, well, we're almost done, so stick around after class and I'll look at your
Will do.
calculator for you. All right, part B, we want to use this equation that we just came up with to answer the question. I'm just rewriting it so I can see it. In part B, they're asking by which year will the population reach 2 billion? So they want us to find T for a specific A, 2 billion. So you'll notice that our A and A sub 0 were in terms of millions. I can't just substitute 2 in for A and have, 2 billion, know that this is billion on this side and million on that side. You always have to be in terms of like the same number unit. So how could we rewrite 2 billion in terms of millions?
It would be 2,000 million.
It's going to be 2,000 million. Which I know is weird and awkward, but we need to make sure we're on the same number unit. And we solve for T. So it's the same process. We're going to isolate the exponential by dividing. We're going to rewrite it in logarithmic form. So this becomes the natural log of 2,000 over 643 equals 0.02346t. Lastly, we need to divide by that decimal. We get the natural log of 2,000 over 643 all over 0.02346. Plugging that into our calculator, we should get T equal to 48.36. But we want to actually answer the question. The question says, by which year will the population reach this? Well, I got T equal to 48.36. What did T represent?
Years.
What kind of years? The ones where it snows a lot?
I don't know.
But you're right, it is years. If we go back and read, it says T is the number of years after 1990. So if T is the number of years after 1990, to answer the question, we just need to take 1990 and add that 48.36. And remember, just like on the last one, we always want to round up here. So it actually ends up being the year 2039. And that is our first exponential growth and decay example.
Figured out my calculator.
Oh, okay, good. What was the problem?
User error. I typed it in wrong.
Oh, okay. All right, well, good. That's an easy problem. All right, so we kind of talked about the test. Remember that we will not have class on Thursday, that you will be taking your exam. And like I said, it'll be available from Thursday at 12 a.m. until Saturday at 11:59 p.m. Be sure to get your Dropbox quiz in and your homework in. And I'd encourage you to do the bonus quiz as well. You'll have your 2 attempts on the test like normal. Anybody? Any questions about anything? If you do have questions and want to stick around for office hours, that's great. I'll be on. Otherwise, everybody else, good luck on your test and have a wonderful weekend. I'll see you on Tuesday.